next we will look into another very important issue in testing, which is known as test completion. So, basically when we are storing the patterns in the automatic test equipment, we need to have number of patterns small less, and if it is but that is not always possible, because it is not that if we use a small number of patterns we will get good coverage. So, that is not going to happen. So, we need to have large number of patterns, but storing them becomes an issue. So, we want to store them in a compressed fashion. Similarly, when we are talking about the response part, so response part also we may not be willing to store all the responses. So, we may like to store some compressed version of those responses. These are the two things that we will look into in this chapter. So, compression will be to look. So, first we will look into an introduction, then test stimulus compression, how can we compress the test patterns, then test response compaction, how can we compact the responses, and then some industry practices, and then the conclusion. Why do we need test compression? So, it is one thing is the test data volume, test time, and test pins. So, you see that if we have got a typical test pattern application environment for external testing, we have got an automated test equipment and there is a memory, and this is the circuit for which we want to test. Now, these test patterns are to be transported from this memory to the circuit, and then they are to be applied to the circuit, and then the response has to be collected. So, one thing is that if this memory requirement is large, then that will increase the cost of the ATE. Similarly, if I want to transfer a large number of patterns over this line, then serial communication is not a very effective one. So, we have to have parallel communication. Now, how many such parallel lines can be drawn, how many such parallel channels can be there or pins can be there. So, that is another issue. So, this cost of the ATE is dependent on the number of these pins that we have, that is the ATE channel width, and the memory that we require to store the patterns. And test time is also increasing because of this large volume of data that we need to transfer. So, test time will also increase. So, it is better that we store these patterns in a compressed form in the ATE, and we transfer the compressed sequences to the circuit, and at the circuit before applying the patterns. So, we have got some sort of decompressing mechanism by which this pattern we get back the original patterns, and then those patterns are applied to the circuit. So, this is the thing. So, what we essentially mean is that here the patterns will be stored in a compressed form, and then before the it is applied to the circuit, we have got another module which we call decompressor. This decompressor module. So, this will be this will decompress the patterns that we have got from the ATE, and it will get back the get back the original patterns, and the patterns will be loaded into the circuit. So, why can we compress test data? Because the deterministic test vectors they have don't cares. So, the ATPG algorithms, they have generated the test patterns where the bits which are not required to be set for particular faults to be tested. So, they are left as don't cares. So, these don't cares can be exploited, so that we can match between the patterns, and a number of patterns may lead to one representative one that can replace all of them. That way we can achieve the test compression. So, this is the situation, the test data volume versus gate count. So, if gate count is increasing in terms of mega gates, so the volume of test data, so it is increasing in terms of gigabits. So, as the circuit size is increasing, so you see this so many million gates. So, this is increasing, the volume of test data is increasing at an exponential rate. So, this is a requirement that we must have some sort of test compression mechanism incorporated. Now, this test compression can broadly be divided into two categories. One is the stimulus compression, and another is the response compression. So, in the stimulus compression we are talking about the test patterns. So, we compress the test patterns so that we need to store less information on the ATE, and the response compaction we mean that we are storing will be compacting the response that we get from the circuit. Maybe I have got 10,000 patterns, but I do not store all the 10,000 responses. So, I store only maybe a part of the responses, maybe in some compressed form, maybe in some modified form, and then we compare we do a comparison with that modified response only. So, we have got this so this response compaction. So, it has got space compaction. Space compaction, it will try to reduce the number of outputs. Like if a circuit has got 100 outputs, maybe we pass it through a space compactor, that will reduce the number of outputs to less, say 10 or 20. Similarly, we have got time compaction. So, time compaction, so this will be reducing the so we do not store the response for all the 10,000 patterns. So, we look into less number of instances, and then we have got mixed time and space compaction. So, that is a combination of these two. On the other hand, for the stimulus compression also there are several techniques. Some of them are code based schemes. So, we use some codes for doing the compression. Then there are some linear decompression based schemes. So, linear decompression based schemes, so they will be trying to use some sort of linear structures like LFSR to perform this compression, and there are broadcast scan based schemes. So, this is the typical situation of test compression. So, we have got this low cost ATE. So, as I was telling that the cost of the ATE is too large, and if you are having if you are using one ATE, low cost ATE, then the cost of the ATE is determined by the memory requirement and the memory that it has and the number of channels. Okay. So, if we are if we are designing a new versions of chips or new chips that are having more more number of test patterns or more number of chip pins to be for testing, then it does not mean that we should go for a new ATE altogether, because the ATE investment will be a big question. So, we have to use this low cost ATE itself for testing this high end chip. So, how to do this thing? So, for that purpose, in the ATE we will store the patterns in a compressed form, the compressed stimulus. So, they will come to the circuit, and before they are applied to the circuit under test, so they are going it is passed through a decompressor stage. So, decompressor will convert this pattern into the stimulus, the compressed stimulus, into the actual stimulus, and then this after this this circuit has given the response. So, it is the outputs are collected by a compactor, the response compactor, and this response compactor, the compacted response will be coming back to the ATE. So, comparison will be done with respect to this compacted response only. The ATE will be comparing with respect to this compacted response only. So, many a time the circuit under test we will call it core. So, this is actually this test compression problem is more vital when we are having core based designs. So, in core based designs what happens is that for the entire system we take cores from different vendors. So, cores are maybe a soft description of the system, maybe netlist level description. So, for a system that has got a CPU, memory and say one IO controller, so we may take the netlist for CPU, netlist for memory and netlist for IO controller from different vendors and integrate onto the same silicon floor to get the whole system. So, to get the system on chip type of concept. Now, in this process, now how do we test the CPU? Like I don't know the netlist of the I don't know the high level description, the structural description of the CPU. Now, I cannot generate the test patterns for that. For the test patterns also I have to rely on the vendor. Okay. So, these are called cores. So, core vendors, they are also providing the test patterns, and they are telling me that okay, if you apply these test patterns and if you get this type of response, then the code has been fabricated properly. Now, so that way what has happened is if you are integrating large number of cores, then the amount of test data that you have, so that is also increasing significantly. And the core vendor, since the core vendor does not know about the situation into which this core will be going to be placed, then they cannot optimize on the test pattern, they cannot reduce the number of test patterns. So, they try to cover as many situations as possible. So, that way the test pattern set become huge, and that test pattern set is given to the system integrator, who takes all these codes and integrate into a system. So, that way the integrator has got no option but to apply all those test patterns. So, that is why this the exponential increase in the test pattern size is their test set size that we have seen. So, that is becoming more prominent. So, stimulus compression. So, as we have said that there can be code based scheme, linear decompression based schemes, and broadcast scan based schemes. Now, code based schemes, there are 4 different examples that we will look into, and they represent 4 different categories. Okay. The first one is fixed to fixed. So, that means so your test stimulus portion that we want to take for coding, that is also fixed, and the code that is generated, so that is also fixed. So, input and output both of their widths are fixed. Then there is a fixed variable coding, where the input stimulus chunk that we take for coding, that size is fixed, but the length of the code is not fixed, that is variable. So, then we have got variable to fixed. So, here we have got this thing, the input chunk length is variable, but the code that is generated, that is of fixed length. And we have got variable to variable, where the both input chunk and the code, they are variable. So, we will pick up individual categories and try to see how those codings can be done. So, this fixed to fixed coding, so this is typically known as dictionary based coding. So, basically we maintain a dictionary of codes, and depending upon the input sequence, so we take the code from the dictionary and use it for coding. Similarly, fixed variable coding, we have got Huffman code, which is a lossless compression, and then this one run length code is there for variable to fixed, and Golomb code for variable to variable. One thing that we should keep in mind, that this test stimulus compression, it has to be lossless. Like if you look into this diagram, so at this point I really want the original test patterns back. Okay. So, this compression, whatever is done, that must be a lossless compression. On the other hand, this side, this response compaction, so response compaction need not be lossless, because if it is lossless, then all the information are anyway there. So, we are not going to save on the amount of data that we are going to transfer. So, this is in most of the cases, this response compaction is a lossy compaction, where we have got less number of output bits compared to the number of input bits. However, in this case, this must be lossless. So, we must be getting back the original patterns. So, the first one is known as dictionary based code. So, for understanding this, so we must understand something called a scan slice. Suppose we have got a circuit that has got this scan chain 1 to scan chain n, and from the ATE, so these test bits are coming. So, test bits will be feeding these scan chains. Now, in each cycle, each clock cycle, so each of these scan chains will be getting 1 bit of data. So, that will get shifted to the next position. So, if there are n chains, then I can if you consider the same bit position for each of the scan chains, so that that constitutes one scan slice. So, in the first clock cycle, the first slice is loaded, all the n chains they get their first bit. Then in the next clock cycle, the next slice will be loaded. So, all the n chains will get their next bit. So, this way this loading will be done. So, what happens is that from the ATE through the channel, I get a B bit pattern. So, B bit pattern, so this is used to index this dictionary, and from this dictionary the corresponding test pattern is found, and that is actually loading the scan slice. So, the idea is that maybe if this is the full test pattern set that has got all these patterns in it, if it is a full test pattern set, then we can say that okay, so we find out the slices. So, this is the first slice, this is the second slice. So, this way we find out the slices. This is the third slice. Okay. Maybe this bit is So if I take the first slice, maybe the first slice is 1 0 0 0 1. That means to the first scan chain I will give 1, second scan chain 0, third scan chain 0, fourth scan chain 0, fifth scan chain 1, if there are 5 scan chains. Similarly, in the next slice, so this is for the first one. For the second slice, I may have 0 0 0 1 0. So that is the next bit that will be fed into the 5 scan chain. So this is the this is actually the slices. So this first actually this is if this is the test pattern, this is the full test pattern. So this full test pattern is going to be fed to 5 different scan chains. So I can say that it is divided into say 5 different portions, and this part is going to feed the first scan chain. This is for scan chain 1, this is for scan chain 2, this is for scan chain 3, scan chain 4 and scan chain 5. Now out of that, if you consider the first bits of each scan chain, so this one, so they will constitute one slice. So this is basically one such slice. Now if you consider the second bit of each scan chain like this one, so that will constitute the second slice. So this is the second slice. So this is actually the formation of slices. Now they are going to be fed to all the scan chains in this fashion. Now what we do in the dictionary, we try to see the for the say for this one, this 1 0 0 0 1. So if I in the dictionary, if I store all these pattern, all the scan chain, all the slices that are going to occur, so if I put them on a dictionary, okay, so this is the dictionary. Now if this pattern 1 0 0 0 1 is stored in this position, okay, then it is sufficient that from the tester I just tell what is the index I. Okay. So this index I is told, so that this decompressor that I said, so this decompressor is actually having the dictionary. So from this channel I just get this index I, and this index I is used to locate the corresponding pattern. Okay. So this 1 0 0 0 1, and this 1 0 0 0 1 will be fed into the scan chain slice, like in this example that we are looking into. So here these B bits that are coming from the channel of the tester. So dictionary is a part of the decompressor. So that particular slice is located, and that slice is outputted onto this onto individual scan chains. Okay, one bit for each scan cell, each scan chain. Now naturally, if if my test pattern set is such that it generates different types of slices, so all possible slices are generated, then of course there is no saving. Okay, so we cannot save anything in the dictionary, because the dictionary will become too large. But if it happens that only few some slices are there, it is not that all possible slices are appearing as part of this test pattern sequence, then of course if the total possible slices are less, then this dictionary can be of finite size, and then dictionary whatever slices we have, so that are stored into this dictionary. So dictionary size is finite, so we can put it into as a part of the decompressor. Okay. So this is the dictionary based coding, so fixed to fixed number of coding. So the saving that we can have is that from the dictionary I am getting B bits. So in the tester I need to store only the B bits, okay, for individual slices. Now from the dictionary, so dictionary size is of course a factor, but otherwise there can be saving. The next one is a code based scheme, which is known as where it is a fixed variable length coding, which is known as Huffman coding. Now you see that suppose this is the test pattern set that we have. Now in that we see that how many times this pattern 0 0 1 0 has occurred. So 0 0 1 0, if you count, so this is occurring once here, 0 0 1 0, then this is once, this is once, then this is one. So if in this way if you count, so you see that this particular pattern has occurred 22 times. Okay. then we find that the next pattern 0 1 0 0, it has occurred 13 times. So, what we do, we find out these individual patterns and count how many times they have occurred. These particular patterns like 1 1 1 0 1 0 1 0 and 1 0 0 1. So, they have not occurred at all. So, their frequency is 0, but others have occurred like this. So, in a fixed dictionary structure, fixed to fixed length coding, what we would have done is we will store all these S0 to S12 these patterns onto the dictionary, and for decoding we will just send the index of the dictionary. But what happens is that for every since there are 12 entries, so for every slice I need to send a 4-bit address. The B has to be 4-bit. So, that increases the complexity, in the sense that the dictionary size and your this thing the bits that we need to transfer will be more. So, instead of doing that, what we can do, we can code it using some Huffman coding strategy. We can code it using some Huffman coding strategy such that the highest occurring pattern, so this will be coded with 1 0, then the next pattern that is coded with 0 0, 2 bits. The next occurring pattern is coded with 1 1 0, next occurring pattern is coded with 0 1 0, like that. So, you see that after when it gets this bits, so when the decoder will get this particular bit sequence, so it will be it will work like this. Say it gets a 0. So, once it gets a 0, so from so if we look into this structure, into say this is the circuit, this is the ATE from where I am getting the bits. So, this is coming to the decompressor or decoder. This is coming to the decompressor. Now, if we get a 0 at the line, then we know that the next bit, so we come to this side, and then we again if we get a 0, we know that we have the symbol that is we are referring to is S1. So, this S1 is 0 0. So, you see that this is the pattern. So, we have detected that the AT is trying to send the pattern S1, which corresponds to 0 1 0 0. Instead of sending these 4 bits, the ATE could send only these 2 bits, and that is sufficient to identify this particular pattern. Similarly, if after getting 0, if I get a 1 on this ATE channel, that means it is so I could not come to any decision. I have to go for the next input as well. So, this is 0. So, if the next input is also 0, then I know that this is S3. So, 0 1 0 is the code for S3. So, you see 0 1 0 is the code for S3. So, if we have come to this point, so we know that this is going to be a this is going to be the pattern that we are looking for. So, this is the way this Huffman coding will work, fixed variable length coding. Now, another, so this way this coding works. So, for all these entries, so they are to be, we have to have this big we have to store this big tree into the decoder, and the decoder will follow this tree to do the operation. Okay. So, to find out the actual code, actual pattern that it needs to construct from the code that is transmitted. Okay. So, that is known as, that is the Huffman code. Now, you see that what has happened is that the patterns whose frequency is more, they have been coded with lesser length code. So, this is its frequency is the highest. So, it has been coded with 1 0, next one is 13. So, that has been coded with 0 0. So, this way the coding has been done, and also we can see that the way the coding is done is that we try to group the patterns. Okay. So, this with S1, S3, S4. So, we write them, we just say this S0, S1, S2, S3. So, we just write them in a sequence, and then the lowest occurring patterns, so they are grouped. So, S11, S12, since they are occurring the least amount of time, so they are grouped into one node whose occurrence is this occurrence becomes 2. So, the individual occurrences were 1. So, I can say when I combine these two into one group, the occurrence is 2. Similarly, S9 and S10, so they are occurring 1 only, so they are combined into 2. So, these are also combined into 2. Now, so after this has been done, so we are actually at this level. So, we have got these occurrences of patterns which are 2. Now, again we combine these two occurrence groups, so 2 and 2, so that gives us 4. Similarly, this gives us 4. So, in this way you see the pattern S0 which is occurring 22 times. So, this is coming at a much higher level in this tree, and in the decoding process, so this is given a code like 10, whereas for this pattern S12, so it is given a code like 1 1 1 1 1 1, so many. So, that is a 6-bit coding. So, this S12 has been coded with a 6-bit coding, whereas S0 has been coded with a 2-bit coding. So, since S0 will be S0 is occurring more frequently, so S0 will be sent more number of times, so it will lead to saving compared to this S12. In the normal case, in the fixed to fixed length dictionary case, what will happen is that both S0 and S12 they will be coded with same number of bits. As a result, the saving will be less. But in this case, since we are doing it on a lesser more frequently occurring numbers, so they are given less code, less white code. So, they are we can have some saving.